Welcome everyone to our 12th and final session for this course, this workshop, Introduction to AI. We have covered a long journey in this course. We started out with a little intro and we said we are going to do some of the core neural architectures. We have covered all the main neural architectures. We did the feed-forward networks, the CNNs, convolutional neural networks, autoencoders, generative adversarial networks. We did the transformers, if you recall. So it's been a long journey. And as I promised to you, this is going to be a journey of 1,000 miles. I hope by now you do feel that you have covered a vast amount of territory. But that territory that we covered, it's not the end of the journey yet. We covered many things, but there are many, many things that we didn't cover. So I just want to quickly go through what are the things that we did cover. We started with the basics. What is AI? How does it differ from, for example, writing a quick sort or a business application? And it's a fundamentally different paradigm that we are dealing with. We took examples like the fact that you cannot tell for example, a car to self-drive or things like that. And so those are examples in machine learning or examples in AI, but you can tell how to learn to drive a car. Very much as you would do with a human being. You don't give a child instruction on every possible scenario that they will encounter when they hit the highway, when your child hits the highway, or children hit the highway, or the roads, for that matter. So what you instead teach this child are the basics, but you equip the child to learn about driving. Okay? So there's a very close parallel between that and AI. You create algorithms that teach machines how to learn. And that is AI. From there, we we observed an interesting fact about one particular class of machine learning algorithms, which are the neural networks. The whole course was predominantly about neural networks. We obviously, because it was abbreviated, just 12-week course, 3-month course, we did not do the entire gamut of machine learning. Those of you who are interested in learning about other classes of algorithms besides neural networks, are there any show of hands? If you are, I will be giving some of these sessions. They will be free summer sessions. You are most welcome to attend those. You'll get notifications about those. Those used to be the course ML100 and ML200 here, machine learning. Pretty intricate and long courses. They used to be 3-month courses. But at this moment, in this particular course, we focused on neural networks. Now, the property of the neural networks that makes them so very effective is called the fact that neural networks are universal function approximators. So I hope you remember this, that we covered. I'll just go through these things. We noticed that with the neural network, you could approximate or solve any problem. It was most remarkable. We did this at Tensor Playground. We went and played with it. And then we also did some labs that showed that no matter how complicated or bizarre a function that you can imagine, a neural network was essentially able to approximate it. Right? Now, in this, somebody asked me a question. Oh, well, isn't that imperfect? Isn't it that the neural networks can only approximate a function? Why not find the real function behind the data? Well, for that, I'm reminded of a famous statement by the great data scientist and mathematician, Box. Box made a statement that is worth remembering. He said that all models are wrong, but some models are useful. What he meant by that is that once data is produced, you may never know what the real function is, but it is probably not of great relevance to know that, practical relevance to know that. Because given a data set or given a finite domain, or feature space, there are literally infinitely many functions that will do an equally good job as whatever was the original function that generated the data. Now pause for a moment and think about it. Whatever was the causative function, the driving function that produced the data, if you treat X as the input and Y as the response, there is some driving force that can be captured in some function. And I'm making a statement that within the domain, within a certain function space, there are actually infinitely many functions that can be just as good a model as what was the original function. And therefore, it's moot to ask, what was the original function? You just need to find a function, any one of the infinitely many functions that is good enough for that data. And that's why you say that anything that can approximate the behavior of that unknown original function is good. It doesn't make it right, but it makes it an effective model. And therefore, Box's statement that all models are wrong, but some are effective. And we have to remember that a statement like neural networks being universal approximators speaks to the fact that it can just about approximate any behavior. Pretty astounding statement as it is. Then, after that, we did the fact that how do the machines learn? We went into the whole mysteries of the gradient descent and loss function. Do you remember that? We also saw that loss functions of simple things like linear regression methods are convex. They have a nice simple bowl shape. You can find a global minimum. But neural networks actually don't have convex or simple loss surfaces. I hope you guys remember this picture reminds you here what those evocative loss surfaces that we saw of neural networks. Right? They have the hills and valleys, they have many local minimas. Right? And therefore, the challenging task of doing gradient descent to the true minimum or somewhere near the true minimum, within shooting distance of the true minimum. How do you get to that? And that brings about this entire thing about optimizers and how do you work with those and so on and so forth. So that is the learning part of a neural network. We also studied why neural networks are universal approximators. And we realized that a neural network is alternating linear transformation, right? For example, followed by a nonlinear transformation. First, you do a linear transformation, a w dot x plus b, a bias term, if you remember, in each neuron. And then we follow it up with an activation note. Now, I noticed that there are some notes on activation functions. I hope you folks studied those notes. There are quite a few activation functions there. And we had some PyTorch and lots of work. There's a Jupyter notebook on activation functions and so forth. So it is remarkable that neural networks acquire their universal approximator behavior or their superhuman power effectively from something as simple as activation functions and just the topology of the network. Right? Many nodes collaborating to achieve a universal approximator behavior. Then I introduced you to the PyTorch programming library. It was a basic introduction. In this part, the first part of this workshop, that is the workshop that you have been through, we were more focused on the theory of the neural architectures. We had to economize on time, and so we decided to cover all the major neural architectures. Part B of this workshop, which will come in fall, will repeat everything we did, but we'll do it purely from a lab perspective, from code perspective, and practical use case perspective. So that is that. We also learned about this very interesting thing. How do the different layers of the neural network learn from the loss function? Loss function is something that, in a way, is much closer to the last layer. The last layer can learn from gradient descent, but how do the previous layers learn? And so we talked about all of that. That was a thing about backpropagation. Backpropagation is a magical thing, as you realize, as we did more and more complicated architectures. Every time somebody would ask, so how does this whole thing learn? How do you decide the weights of that? And the answer almost always is just one phrase, backpropagation, isn't it? And it is almost like a magic wand. Given this magic wand, no matter how complicated an architecture you create, a neural architecture you create, so long as the gradients can propagate, so long as it remains differentiable, I'm using a little bit mathy term, but I hope it means something to you. It means that like all of the nodes, you can take the gradient, activation function, take the gradient, so common sense things. Then you can actually train the network using backpropagation. We obviously went through the solution to the problem that I gave you, PyTorch homeworks that I gave you. We talked about optimizers, and again, a review on how machines learn. There are methods like momentum-based optimizers, which I don't think we covered, but we'll do it with lab. When we do the lab part of this counterpart of this workshop, you will see the effect different optimizers have on how well they solve a problem. The same problem we'll try to solve using different things. Now, I parked all the theory of the optimizers here for the adventurous souls who want to go and learn more about it. Optimizers are a whole world in themselves. I introduce you to the simple gradient descent, but there are many, many variants of it. The entire PhDs, the entire textbooks in graduate school, the entire courses given to optimization in this field. Like, for example, Stanford has quite literally 2 courses on optimization. The convex optimization 1 and 2. Right? And there's this book. And though the paradox is neural networks are non-convex, but still this theory is quite useful and worth learning. We talked about the loss function, how to quantify errors. And we learned that for regression, you can use mean squared loss. And for classification, you could, for example, use binary cross entropy loss if it's a binary classification, or just a negative log likelihood loss. And there are other loss functions that I sort of mentioned, I've enumerated, but we didn't cover because we had to move fast. Then we went to a different neural architecture from the standard feed-forward architecture called the convolutional neural networks. The convolutional neural networks, the key sort of, if you remember, it's an architecture that induces a bias. Locality is a strong bias. And you hierarchically, the hierarchical nature of feature is a bias, and so on and so forth. So we covered CNNs in quite a bit of depth. We learned about the key concepts: convolution, pooling. Do we remember that, folks? Convolution, pooling, and then deconvolution. So we went through some code with convolutions, but again, we did code, but we'll go through a lot more code in the coming part 2 of this workshop. We talked about deconvolution, and then we did neural architectures like the autoencoder. Autoencoders. Autoencoders are encode and decode. The encoder projects does a nonlinear projection of the input data to a latent space. The latent space traditionally could be of lower dimension. And so it is a process of extracting the most meaningful latent representation. But you also have overcomplete autoencoders. Now, the autoencoders you can build out of dense layers. You can build it out of CNNs. And as you will learn, you can also build it out of transformers, right? Or throw attention into the mix and so on and so forth. But more of that later in the second course. We can have overcomplete or sparse autoencoders, denoising autoencoders. We can have then contractive autoencoders. We can have variational autoencoders we talked about. And we, in glance, with just we just had a glance at something called vector quantized variational autoencoders and a little bit about the Wasserstein distance. We talked about little bit about generative models, how they can be used for generative models. All the variations are generative, and also that they are used for example, in the architecture of diffusion models. You use a UNet, which is essentially an autoencoder with residual links. So we talked about that. Variational autoencoder, we gave some time to, but I think I haven't put the video here. I should do that. I'll find it and put it. Then we talked about generative adversarial networks, the analogy we gave is that it's an interplay between a cop and a counterfeiter, right? A crook and a cop. The crook is trying to hoodwink the cop. The cop is trying to be a better cop and catch the fake. And in the process of playing the adversarial game or a min-max game, they both become better. We saw that in the playground for adversarial for GAN, which I hope you all played with. And we saw the uses of this adversarial network, many things. It's a generative model. It can generate data. It can generate people who don't exist, faces. Do we remember the website? This person does not exist. Quite remarkable, isn't it? And then we also saw that it can do other things, generate synthetic data. Is one of the biggest generators of synthetic data. Very practical use. And then we saw a neural style transfer. You could do a neural style transfer by taking, for example, any picture and then imposing Picasso style or Van Gogh style or anybody's style on it. Right? Very remarkable feats that these things do. Finally, we learned about what is attention. Remember, when we talked about attention, the key ingredients is attention, given inputs, multiple inputs. Attention requires a context. That context will help us pay differential weightage or attention to different inputs. You pay more attention to this input than to that. Right? So that is the concept of attention. Then we come to what was perhaps the most important architecture that has emerged in the last few years, namely the transformer architecture. The transformer architecture underpins all of these so-called chatbots and so forth. So we went through the explanation of the transformer architecture. And today, we are going to do the new topic of encoder-based and decoder-based architectures within the transformer architectures. So that's a summary of where we are. Now, let's going back to our code, our thing. We covered this landmark paper, if you remember, for transform that ushered in the transformer, namely, and I hope you remember that as a recap, attention is all you need. Where did it come from? It came from the fact that in Google, people were trying to do language translation and other things, build language models. At the time, there were three big architectures they had discovered. There was the feed-forward network, there was the convolutional network, there was the recurrent neural network. And then finally, attention came along in 2014, actually. And so people said, let's put that also into the mix. So there were four key ingredients that they were throwing into the mix. You can't get rid of feed-forward because it's there. It's the one that brings in your nonlinear transformations and so forth. And well, you always need it to do changing from one dimension space to another dimension space. But then they were trying to create a language models using a mixture of convolutionals, recurrence, and attention. And they were going to call it the cargo net or something like that. From convolutionals, CO, right? And recurrent, and then Google net, I suppose, cargo net of Fortunately, as they were researching, they realized that what happens if from this architecture we throw away the conv? They realize, well, it continues to perform just as good or better. Then what happens if we throw away the recurrence? Now, that was sacrilegious in those days. Even though attention had come out, all the language modeling was done with recurrent geometry, most of it, or with convs. And so nobody had thought of throwing away the recurrence. And they found, to their surprise along the way, that you could throw away the recurrence also. And so what remained was attention. And therefore the title of this paper, Attention is All You Need. It obviously was a landmark paper, came out towards the end of 2017, December 2017. By early 2018, people knew that the world had changed. The power, the capacity of this model was amazing. And yet, if you read the paper, and we went through this paper the last time, it is made up of your encoder, decoder. Each encoder has multi-head attention, which means many pillars of attention stacked in parallel. And each of the pillars has lots of attention stacked one on top of the other in serial. So that was your multi-head attention. And what it contained, the key formula was, and then we called it self-attention, because it's not just attention, it's just self-attention as it is used here. Every word in the sentence pays attention to every other word in the sentence. Now, what were the key characteristics of this architecture? Massive parallelization. Now, you remember, if you rewind back to 2017, at that time, computer vision was having a great day. They were benefiting from this massive NVIDIA GPUs, which were heavily parallel processing engines. But the language models were not benefiting from it. The language models were still very sequential. RNNs are inherently a sequential engine. So one of the big breakthroughs that this paper brought is, because all the tokens go in at once, they have to, there is no choice. And each token needs to pay attention to all other tokens. It opened the floodgates to parallelizing and speed up. And so this paper, if you read this paper, you will see that the flavor is a lot about how it leads to parallelization, right? And efficiency and performance. You can train and you can do things much better on this hardware. So the results spoke for themselves. The transformers began to beat all the previous architectures in benchmarks. But that was not the key contribution, the fact that it beat it. The key contribution is it opened the doors to parallelization. But much more than that, and what perhaps the creators themselves didn't realize, that what they had stumbled upon or discovered wasn't yet another architecture that brings up speed up, but would turn out later. And increasingly, we are finding, for reasons that even today are not very clear, transformers are in some sense of fundamental architecture. They bring about an empowerment, an ability to build or solve problems that you would typically not imagine with previous architectures, to a level of accuracy, to a level of performance, model performance, that was absolutely unprecedented. Many of you remember that it used to be a joke giving the previous language models 10 years ago to translate anything to anything. Right? Today, the translations are not perfect. They're still pretty imperfect, but at least you can get the sense of what was spoken in the other language, isn't it? And obviously, we have all played with ChatGPTs and the Geminis and the clouds, and we can all vouch for the fact, and now, of course, Llama, open source projects, and we can all vouch for the fact that they are very, very effective machines. Now, in this architecture, though, transformers were not a complete blessing. There is a cost that came. In this equation one that you see hiding Q dot K, a quadratic term. And we talked about this quadratic term. And what this quadratic term does, this term, is it makes the compute quadratic in the number of tokens in the sentence that goes in, text that goes in, isn't it? So if you send 10 text, let's say that the computes are in the order of 100. If you send 20 tokens, words in the sentence, now it becomes 400. If you send 100, which is just 10 times 10, it becomes 10,000. Right? So the compute grows quadratically, and that requires a lot of GPU. So yes, you can parallelize, but you better have the hardware to do it. And you can see that the GPUs that are, even though the GPU, the compute power of the GPUs are growing much faster than Moore's law. Somebody said, and I think this is fairly accurate, that the compute power of the GPU, if you just look the doubling rate, it seems to be doubling every 8 months. Well, NVIDIA doesn't, and these people don't exactly release a product every 8 months, but it is effectively as though it's doubling every 8 months. Right. So those of you who are doing the bootcamp know that you're sitting on your 4090, and 4090 will soon be superseded by 5090. The Grace Hopper has been replaced now with the Blackwell, which is supposed to be between 4 to 8 times faster and more powerful than the state-of-the-art chip. Today, the Grace Hopper goes for $30,000 to $40,000, and yet Blackwell is coming, which will be close to 8 times more powerful than that. Between Grace Hopper and Blackwell, I believe the gap is about a couple of years, year and a half or 2 years. Right? So things are moving that fast. Now, today, what I would like to do with that summary of what we have covered, not just in the last time, but in this course, I would like to request you the following. I'm going to give, today's topic will be the final topic. We'll go through some major transformer architectures. We'll see its use cases, many use cases. I'll give you a tour of what all things you can do with these transformers. Are we together? And with that, we'll conclude. But I have a request. In the break, there is a small end of course survey. Do you notice that workshop feedback? Can I invite you to spend about 10-15 minutes in the break to fill out that survey? So,
I don't know if we'll have time, but I'd love to kind of maybe we could spend maybe 5-10 minutes talking about the text to audio and video portion of it.
Yeah, I will today. I will do that. This is what I'll do. I'll give you a sense of where we are going with all of this. And in many ways, the next, the practical part of the bootcamp will not just be practical, not just the lab version, but it will also give us time to bring in, like, for example, the diffusion model, text to images and text to video. We will actually do labs in those. So it is very much within the scope of this course. So today I'll touch upon it. So any questions, folks, before we start?
So you're going to cover that when you enter the text and then image, that also will cover.
That's diffusions, yes. I will cover that today.
Asif, one question. When you're talking about tokens, so these days all the large language models are coming up with some token limitations, right? So the tokens that you spoke in the attention paper and the limitations that these LLMs have, what is the correlation between them?
The tokens that I spoke in the attention paper and the tokens that are, say that again?
The token limit that ChatGPT and
that is
Llama
right.
has.
It is exactly that. It is exactly that. So let me explain it. Let me take off my jacket. I'll explain it to you guys. Let me start writing now, and I'll explain it on the writing board. So guys, yeah, this is our last session. Let's keep it interactive. To make sure that you don't feel tired, I got you guys lots of sugar today. There's ice cream. So it's in the break room, in the fridge. Do please make sure you finish it all off. So you're well sugared. See, we talked about the fact that if you have a transformer, let's say, let me change the color. See, you have a transformer. It has an encoder. It goes into a decoder. But what goes in? The cow jumped over the moon. Right. Now, this is tokens. How many tokens there are? This, and this last. This thing. So let's say 1, 2, 3, 4, 5, 6, 7. 7 tokens going and 8 tokens going. Now what happens, I mentioned to you that given a transformer, because of the KQ, the dot product here, then I'll just to be completely accurate, I'll just wrap it up in the softmax function, actually, softmax. Max function times V. And I'm dropping all the subscripts. I hope you understand, right? So what happens? How many keys will be there? Number of keys, is 8. Number of queries, because each token is going to pay attention to every other token. So that will be number of queries, 8. And so you have 8 cross 8, 64 compute. So what happens is that, now imagine that this was not 8, but suppose it was 800. Right? You realize that if I add 2 more zeros to it, then I'm adding 100 times 100 is 10 to the power 5. That is 6.4 million. This scores, these are called scores. 6.4 million scores will have to be computed in every attention head, right? As the information propagates, input propagates to them, isn't it? And now what happens is, that is what limits a transformer. So given a transformer, transformers are made to fit in on certain hardware. Right? So let's take the basic version of a transformer. And by the way, a lot of research has happened. And now whatever I'm saying is a very simplified version. And people have found workarounds to this. But the simple picture is that you cannot make your token length too large. Why? Because if you make it too large, you basically won't be able to handle it in your neural architecture. It just won't scale well. It just won't work well. So what these machines do is that they, right off the bat, when you give it, they just truncate it. So suppose you give it this input, they will just take the amount that they want. For example, for the original BERT, we will talk about one of them. It was about 512 tokens. It will say we won't take more than 512 tokens. Right? And the number has been increasing, getting bigger and bigger. And now one of the big developments in the last 6 months has been people have been increasing this length. So the answer to your question is yes, the two are related. They're exactly the same. That's what it is. Right? The token that people talk about, token limitation, has to do with literally how much you're allowing the input, how much you're allowing to go into your transformer. Yeah.
So the 512 is the KQ. The limits.
That is right. You're basically saying I won't allow more than 512 tokens to go into BERT.
And that is a combination of key and the query.
No. Five input words. No? The sentence. As far as the external world is concerned, when you are sitting upon a model, what is the maximum number of tokens you're allowing to go into the transformer in the first place? Yeah.
How are they optimizing? They're increasing the context window. So
Oh, yes. So nowadays you must have heard that people say, hey, the context length is 50,000, 100,000, or 1 million, 1.5 million. And now there's a recent research paper that it is infinite. How do they do that? What are the tricks they use to allow for infinite context length? Right? So that becomes a little bit of an advanced topic. And I will address it in the next course. But simply put, it is hard. Right? You need to do clever things, pretty clever things, to make it possible. Right? So let's leave it as that. But yes, just know that these transformers have, but the token length now inputs don't have as much of a limitation as people imagine. They have become pretty efficient. Mostly, if you look at these models, they are very generous with input tokens, but they are not so generous with the output. They will still limit the output at 6,000 or 4,000 tokens or 2,000 tokens or something. Or try to coax any one of these, like the free version of ChatGPT, to produce anything more than 2,000 token, and you will notice that you're soon beginning to hit a wall. It keeps on refusing to go beyond that. Right? You say, give me a longer answer, it won't. Right? You must have seen that. And then the commercial versions of it, the paid versions of it, are a little bit, they do end up giving you longer answers, but you can't typically ask them to produce an answer, which is 1 million tokens. So that goes to another problem, which I'll talk about. See, what happens is that, okay, this thing is again misbehaving. Give me a second, please. Okay, let's try a luck with this. Okay, much better. So what happens is, let me give you the argument. This is how it is. And Jan LeCun calls it the diffusion of errors. It's a concept, and I'll just stop with that because we have a lot of data to cover. In a simplified form, and again, I'll give you the simplified argument. Let's say that you have a machine. You ask a question. Right? Some query prompt goes in. And what is the machine doing? It is emitting token by token, next word. Now, at each moment, it has a certain probability that it will not give you the best token, the best answer, right? So imagine that in some abstract word, the best answer exists. There is a certain probability that it will go astray. The next token would not be what you want, right? So let's say that this is the probability of the error at any given step, Pi. Are we together? Probability of error. Or let's put it the other way around. Probability of getting the correct answer is something at each step. So let's say that it's supposed to produce the cow jumped over the moon. What if it suddenly, by mistake, instead of jump, produce the word swam? Now what happens? The cow swam. You remember that the decoder part of it, uses the token that it has produced along with the prompt to produce the next word. So what will happen to the cow now? Will it be jumping over the moon or will it be swimming across the river? Yeah, because you have made a fatal mistake. Right? The machine ended up producing swam, and now it has to take that into consideration to produce the next token. Right? So what it means is that if you have a certain very high probability that you'll get it right, let's say that the probability that you will essentially come up with the right word is 99%. Right? Let's take that, 99%. So it means that the probability that at any step, first token, the probability of error is 1%, right? 1 over 100. And this is 99 over 100. So now suppose you generate 100 tokens. Right? What is the probability that all the 100 tokens came out correct? It would be 99 over 100 times 100, isn't it? First token must be right, second token must be right, third token must be right. Now that is 0.99 to the power 100. Can somebody tell me what is that?
That's smaller than 99.
Much smaller than 99. How much? Make a guess. 80%, 90%?
0.7.
37% it says.
Yeah, it is already very unlikely. It has gone below 50% to be right. 0.99 times to the power 100 actually should be even smaller than 37%. What is it? Sarah, did you do it on the computer and see, or on your calculator and see?
I did it on the calculator, but 0.99 to the 100
Is
0.366.
37%. Okay, 37%. Okay, and so up to 100 tokens, you still have a reasonable chance of getting something sensible. What happens when you ask it to produce 1,000 tokens? Now let's do the same thing to 1,000 and see what happens for 100. For 100, we get this. For 1,000, we get, what do we get? Anyone?
Or 1,000th of a percent. 0.0004%.
0.004%. Yeah. Okay. 3 zeros or 4 zeros? Okay, whatever it is. But you realize that this is basically zero, right? So there's this problem with machines that, the chance that every single step it will keep producing the right sensible answer keeps decreasing. Is the diffusion of errors. Well, this is an oversimplified picture to convey to you that it is far harder to produce long sequences of correct text. It has a chance of getting misled. Right? One fatal mistake, and then it is, these things have a way of self-correcting a little bit, but still, they're fighting a battle that is against them, isn't it? And so that's the other limit. That's the other aspect of the token limitation. That's why most of these, because they want to produce sensible answers, they're rather parsimonious in the amount of tokens they produce. Anyway, so that is that. And with that, now let's go to the topic at hand today. The topic that we'll talk about is what can we do with these transformers? What can we do with these? With these transformers. That's the thing. Now, through popular usage, we have, of course, heard what we can do. But let's look at one thing, that a transformer has an encoder and a decoder part. Sometimes people just use the encoder part. Let's take only the encoder part of the transformer. So what happens? Tokens go in, tokens being a word, the cow, jumped. And what will happen? For each token, 1, 2, 3, 4, 5, 6, 7, 8, you will get eight H states. What you do is something clever. You and encoder. One of the first thought that people have is that what can we do with encoder only?
Latin states.
Yes, so it will produce a. See, what happens is that when you reserve a special token in the beginning and end here, and of course end of sentence. What you do is, and then you can pass another sentence like something else, end of sentence, EOS token. You can do, but anyway, let's leave it like that for the time being. I'll just say if you just send encoder only, you will get hidden states for each of them, right? Let me call this the 0th token first, second, H0 all the way to H8. You will get some hidden states, attention vectors coming out of the encoder. Does that make sense, guys? Now, what can we do with this? It turns out you can do quite a bit of things with just encoder only. And the first family, or very widely successful family of transformer use cases came from something called BERT. It was encoder only family. BERT led to a whole sort of its own BERTology. There was BERT, then there was a distillation of BERT, distill BERT, there was an improvement on BERT, Roberta, and then DBERTA, and so on and so forth. There are quite a few BERTs around of different sizes, base, large, etc., etc. Now, but they all share one common set of ideas, and I'll talk about it. What the BERT paper talked about, yes.
Just a clarification. So the hidden states are it's a collection of tokens. Not every token gets converted to a.
Every token gets converted to its own hidden state. No? Remember, when we talked about attention, what happens? Every token becomes a token vector, embedding vector, and its position vector. It goes in, it pays attention to every other thing, but at the end of it, it produces outside the attention head, it produces its own attention vector, isn't it?
Yes. But I was thinking in terms of you have tokens and you have sentences, they're not the same thing.
No, a sentence is made up of tokens, no words.
And I thought those sentences are the ones that gets converted to.
No. I know why you're getting confused. See, Vasanthi, what you're saying, that is a particular architecture called the sentence BERT that you encountered in the book, which you're confusing the two. Now I'm talking of the very basic transformer. Just think, how does the transformer work? Isn't it? That's it. And by the way, the way the sentence BERT does it is, all these tokens that come out for all the words, all the tokens become vectors. It just takes the average of it to create one vector out of, let's say, all these vectors, right, in that particular implementation. So we'll come to that later. But at this moment, realize that each token has its representation, right, attention representation, including this here. So the first architecture that came out was BERT. What BERT did, and the way the BERT was trained was very clever, actually. What they did is, they said, okay, we will always send in 2 sentences. So each sentence will be made up of its tokens, right? Let's say that the sentence 1, token 1, token 2, etc., token n. Then you have end of sentence, token. Then the next sentence of different length. And what we do is we put a special token called the CLS token. It's just a placeholder token, meaningless token. And then this is a sense. So maybe this could be it was the best of times. And maybe when you say second sentence in the world of natural language processing, is different from grammatical sentence. It is your choice what you call your second sentence. So we will choose to call the second sentence, it was the worst of times. Let's say, right? So we have two sentences. Now, as far as the encoder is concerned, if I were to feed this into an encoder, all of this into an encoder, transformer, the encoder part of the transformer, what will it look to the encoder? It doesn't care what it is. To it, it is just a stream of tokens, isn't it? So suppose this is Tn and this is Tm. It will say I got a n plus m plus 1 for this and 1 for this plus 2 tokens. Does that make sense? CLS is a special token in the beginning. EOS is a, or maybe 3 plus 3. Let's say end of here also plus 3 tokens. 1 for this.
Even if that doesn't make any difference to input.
No, it doesn't make. It's just a dealing. And now comes an interesting thought. Now you'll ask, why did we put a CLS token here? You'll see.
Do you have a CLS in front of the second sentence? Or
No. Only in front of the entire sequence. So what happens is that each of these becomes its own hidden state, right? These are all attention vectors, right? Let me just call it A1 to whatever, A, K, where K is equal to...
Attention vector is this?
Come again?
When you say attention vector is the word vector along with the positional vector.
Yeah, word vector plus position vector. No, that's the input to our... No, you're getting confused. See, remember, into the transformer encoder goes the word embedding
And the position.
plus the position embedding. It goes in. At the end of it, what comes out is the attention vector from the attention head. In reality, it goes through a feed forward nodes. Remember, we talked about it last time. It goes through a few feed forward nodes. So even that gets transformed. So let me just call it hidden state. Let me just not call it attention vectors, but it is basically some transformed version of the attention vectors for each of the words, right? So that is what comes out. Now,
one question: the number of hidden states will be lesser than the number of tokens, right?
why?
Because
It will be exactly matching that.
well, when you did the encoder and decoder, you told
Oh, no.
compresses, right? So
Sorry. This encoder of the transformer is very different from that encoder that you are thinking of, the autoencoder.
Okay.
It's a different architecture. No? Okay, guys, I feel that I need to review the encoder, the whole transformer architecture again. See, what is the attention?
That I understand, but it's just that that encoder. Okay. Yeah.
This is a different thing, a completely different beast. Right? Remember, in a language model, you pass in a text. What does the encoder in a language model of a text do? It creates a hidden representation, right? And that gets decoded to produce output. In a language model, even in an autoencoder, but in a language model specifically, you're silent about the size of the hidden state. For the case of a transformer, in the classic transformer, for every token, there is a hidden vector. All of it come out together, right? So the encoder will produce as many hidden vectors as there are tokens in the input. You should remember. And
but
so
in the case of image encoder, decoder, the autoencoder, that's not the case.
that is,
it can be more or less.
Yeah, that is different. Yes. That's a completely different kettle of fish. Right? So let's come here. You get these hidden states, and you mean, can we use a feed-forward network or a CNN, the old autoencoder pieces, as sequence-to-sequence model? People have tried that, right? And the success rate isn't that great. Yeah, in fact, that's what I was saying. Before the transformers came, convolutional net, 1D convolutional nets are quite popular. But not really in I mean, they would try to do language modeling with that, not with great success. For decoder, they would still use RNN or something like that. But see, guys, transformer is a completely new architecture.
But within the encoder, when you transform it itself, we have encoded both ways. But within the encoder, we have the sequence of RNA.
No.
That leads to the.
No. Let's go back again, guys. Okay, we need to revisit our previous paper. Look at this. This is your encoder and decoder. Left-hand pillar is the encoder, right-hand pillar is the decoder. Do you notice that nowhere is there a CNN or RNN or anything like that? Nowhere. It is only made up of attention heads, which is why the title of the paper is Attention is All You Need. You see that? No? And that is a landmark discovery, that you can build a language model by throwing away all of those things and just using attention heads. Lots of attention heads, multi-head attention. Go ahead.
So the hidden state and embeddings are the same. Yeah. The difference.
See, anything that a neural network produces is a hidden state, okay? Unless it is in the output layer, and therefore it is. If you really want to use it, it exists in some vector space, and therefore is an embedding. And so, in some, it is interchangeable. Though when people say the word embedding, they often imply that that vector space into which the hidden state vectors exist has some richness to it. Like, for example, in the sentence transformer, the sentence encoder, they were semantically rich.
This one question, when you have this multi-head attention, we watch that video, they were saying about multiple perceptron layers. That multi-head is the one where multiple perceptrons, because we could not relate to either a feed-forward network or how parallelism is happening.
Okay. I understand where the confusion is coming from.
Yeah.
See, okay, let's go back to the basics and review what we are talking. First is, let's go to a simple attention. So a simple attention head is, let's look at this. Just, let's look at this guy. We'll look at only this guy. Right? So what is this? This is your classic K, Q dot product, right? So this is it. And obviously there'll be a scaling factor and softmax function, but let's look at that. KQ, multiply, scale it. Scale is the square root of D. Mask is, forget about the mask. In the encoder you don't. Softmax, this is the softmax. So this is this part. Scaling is what part? Scaling is this part. Square root of D. Matrix multiplication is K dot Q. Softmax multiplied by what? The V. So this is one. So this is one attention. What you do in reality is, now remember that this is a linear transform. And then you softmax it and all right. Softmax just scales it down to a certain limit. But you also, right after this, the output that comes in. So suppose I take the cow jumped, etc. Each of these words Each of these words can act as a query vector, and therefore it will develop its own attention vector. Attention the, attention cow, attention jumped. These are all vectors coming out of this. Now what you do is at that particular moment, I'm giving you the oversimplified version at this particular moment, that if there were no multi-head, what you would do is you still pass the inputs through feed-forward networks. Feed-forward networks are also called what we call feed-forward networks. You know this kind of things. Remember, we are familiar with this kind of a network. If you remember, each layer having connection to the next layer, every node of the next layer. This is also called multi-layer perceptron. Some multi-layer perceptron. So the output of this, you're feeding into this. That's all it is, to get a final output. That's all. So the reason you do that is it is like elasticity, it's like flexibility, the ability to deform and transform and project.
The question is like when we say softmax in the feed forward, that is the end. Right?
Yeah, but that is not the only
here
place you
softmax
use.
is in-
Everywhere softmax is used. Right? So when people think of softmax, it isn't just in the output layer.
It's not.
No. You can use it. It's used heavily throughout the neural architecture. Are we together?
Yeah.
Right? And now what happens is, now look at the multi-head attention. What you do is, so linear, KQV, these are linear transforms, linear. You do a scaled attention, all of them. Then what do you do? So suppose you had one head. This will produce let me call it, from the first head, you get the. You also get, suppose you have multiple copies, different copies of it. The same word token will have from the second head also coming, third. So what you do is you just concatenate them. So this is the concatenate vector. Why would you do that? Why would you make the vector longer? Right? Arrays less longer. One version of the cow comes from this head, another version of the cow comes from the other head, and the third version of the cow comes from the third head. Why would you concatenate that? It turns out that because of the magic of backpropagation and the way these networks learn languages effectively, they will be forced to pay attention to different aspects of the language. Or one, for example, it may be more focused on the grammatical aspect, one may be more focused on the semantics, so on and so forth. Right? And so from the cow, you want all aspects of cow to come together and join forces. Right? They go through a linear transform, and finally you get a ultimate total cow. Let me just call it total cow vector. Right? So that is the use of multi-head attention. But at the end of it, your now what is the encoder made up of? A pillar of multi-head attention. One multi-head attention, right? So multi-head, this is one, let me call this MHA. Okay. And now what you do is you create MHA. One output of this goes to MHA 2. And while you are at it, keep going as much as you want. So they typically in the first version, they went 6 deep, 6 layers deep. BERT, I think, went 12 and 24 layers deep. Right? You can pick your number. So that's why people just put the word N, because every guy who creates an architecture has its own choice of how many they'll stack on top of each other. So by the time you have stacked, you realize that you're looking at a bizarrely big neural architecture, isn't it? Like this is really big. Now that hopefully gives color to why some of this these transformers, when you download them, their number of parameters are in hundreds of millions, right? And billions nowadays. Oh, billion is small. Nowadays, you're talking about hundreds of billions and trillions. Yeah. So so now I hope we clarified that. Yes.
This might be very basic.
one word goes through one MHA and through all the layers of the
Yeah.
MHA. And then the next word will go through the same thing.
Yeah, in parallel, they are all going through
parallel,
that.
okay.
Yeah, because remember, they have to go in parallel. Otherwise, how will you? Attention means the word is paying attention to other words.
So there'll be like parallel stacks. Of MHAs, is that?
No.
Yes.
See, you have multi-head attention in parallel, right? The same, all the words, all the 8 words. The cow jumped over the moon.
Yeah.
They will hit each of the attention heads at layer 1.
Yeah.
Right. So, how many vectors will come out of that? 8 attention vectors will come. And let us say that multi-head, you had 4 heads in parallel sitting there.
Yeah.
So then there are 4 versions of the cow, there are 4 versions of the moon, there are 4 versions of the jumped.
Yeah.
They all come. You do the concatenation operation in forward, but then the cow of this and this and this and this all get concatenated. Okay, right? But then ultimately you produce the cow attention vector, which is the concatenation of the attention vector from these. You have a linear transform, which in other words, you feed it through some feed forward network while you're at it. And then what happens is you're just done with one layer. Now you're ready to pass it to the next layer. And the next layer, and the next layer. Right? So what happens at each layer is all the words go in, pay attention to each other, figure things out, and they pay different kinds of attention to each other in different attention heads. Right? In one attention head, they may be more grammatically sensitive. In another attention head, they're looking at something else. Then they get concatenated and all these things happen. So a very complicated set of dynamics is taking place. Experimentally, empirically they found that this works quite well. But why does it really work? What is the mechanical explanation of why this whole thing works so well beyond anybody's wildest imaginations? We don't understand. All we know is we created something quite complicated, made out of simple pieces, right? And the whole thing works amazingly well, right? That's that. In fact, it's so well that people are now fearing AGI. Okay. So, yes.
So the feed-forward network, what's the typical number of layers they have? Is it one layer or is it going to be multiple layers?
You typically don't have one layer, you'll always have multiple layers.
Okay. So in the case
that is why people use the word, like for example, that video that you guys have referred you to, use the word multi-layer perceptron.
Yeah. Okay. So in this case, the number of words going in is, so let's say for example 501 tokens. So it's means that you have like an output, the neurons will also be like 501.
Yes.
Right? So it's basically sort of we are not, I don't know, like internally, like they may be like reducing it and expanding it, but ultimately, like when they come out, it is going to be like the same number of
yes, exactly, absolutely. From the encoder at the top of it, exactly the same number will come, except that they have all been inspecting each other.
Yeah,
attention means staring at each other.
The word sounds frustrating. Say parallel, because this MHA goes this MHA. Parallel, the 8 goes to 1, 8, another 8 goes like this way.
Yeah, exactly. 8
is in parallel.
Yes, exactly. Because so, guys, this architecture, this transformer architecture is very, very important. And over the summer, I'll give very slow breakdown explanations for this. It's coming up in the coming weeks. Right? At this moment, I've given you enough, but I'll break it down small pieces. And when we do it in code in the workshop too, we'll literally build the transformer from scratch. This entire transformer, we'll write the code and build it from. So when we do it in code, you will literally see the flow. Are we together? It will become very concrete, very real for you when we ourselves build it, a simplified version of it.
One last thing. When you said 612, the number of cycles where this MHAs go back. So for example, once we do this one and then a back propagation happens back to them for layer.
No. See, what happens is that it's a pancake. One set of heads, multi-head, another layer of multi-head, another layer of multi-head. So the input that goes in ultimately forward passes through all of them. Right? Output gets created. Let's say that you were back propagating based on that, some loss function. It will then run backwards through all the layers.
In each MHA, 1, 2,
Yes.
3, 4. Oh, okay. Now,
Now you got it, right? Any other questions, guys, about the fundamental transformer architecture? This architecture, takes a little getting used to. It is so unlike and unusual that the questions that you guys are asking are very natural questions. You realize that it looks, if you're used to feed-forward network, your convolutionals, your autoencoders again, you stare at this and the whole thing looks completely different, isn't it? And bizarre in some sense. Yeah, go ahead.
When training this asset, that's why even slightly some of this is gone on me. When training the model like this, for instance, to say that the tiger ate the cow.
The tiger ate the cow.
Yeah, and similarly the tiger ate a bison. Right? You find this happening a lot of times. The training data is being trained on generally available tools, which is why when this is repeated over millions of phrases, words, and all that, the cow and bison vectors finally appear somewhat in the same vicinity of each other. For instance, and let's say a tiger and a lion.
No, Mahesh, you're completely mixing it up with the sentence encoders in the boot camp. It's nothing to do with that. All we are saying is, when you feed in the word, the tiger ate them, and happens to be, the next word happens to be, anyway, why don't we wait? Because I'm going to come to that topic I'm going to come to. All right, guys. So at this particular moment, do we understand the basic transformer? Right? What does the decoder do? It decodes and produces the next token. Right? So now one of the questions fundamentally is, how do we train this beast? Right? It's a pretty mighty complicated architecture. How in the world do we train it? So that part we'll get to now. Let's get to it now. So BERT is one example of how you train. You take only the encoder part of it, the first half of it. So what happens when you give it text, one sentence and sentence 2, look at this. Let's recapitulate. This is where we were in 2 sentences. Sorry, we give it this and this. Then what happens? As far as the transformer is concerned, all it sees is a series of tokens. Does that make sense, guys? Now what will happen? Everything will start paying attention to everything. But there is one token here that has no meaning whatsoever, no significance. Which token is that?
CLS.
CLS. So what will happen? There is no rhyme or reason for anything to pay attention to CLS. Right? They will say, I don't know what this is. But CLS will be impartial and pay attention to all the text and figure out what exactly are the sentences saying. Does that make sense? And in some sense, therefore, in a sort of a hand-wavy way, we can argue that the CLS token will contain the essence of both the sentences. Isn't it? It will be. So now let's see what we can make of it. So suppose we take just the CLS token. So it has produced its own hidden state, CLS, isn't it? And every token has produced a hidden state. Now we have a choice. Just look at the encoder part of it. And this is how BERT was trained. You have one sentence and you have the second sentence. You have the CLS, you have the end and end token, put slashes for that. This becomes HCLS. And then you have all the other tokens, H1 to HN. You have 2 choices, guys. One is you don't have CLS at all. You take the average of all the tokens and you produce a vector. If your job is to produce one vector out of all these arbitrary number of vectors, because you don't know how many tokens were there in the sentences. But you have to produce one vector. There are two ways of doing it. You can just add up all the vectors and average them, or you can just look at the first token. Right? BERT architecture chose to take this hidden vector and said, okay, we will consider H, this hidden state of the CLS token, to be representative of the information in the text. Are we together? Now, what can we use it for? What they did, how do you train this machine? Here is the fun part. What they did is, they said, first we need, if you create this encode the BERT with lots and lots of this multi-head attention, you end up with a bizarrely big neural network with millions and hundreds of millions of parameters. Make sense? That needs a lot of data to train. And where do we get that data to train? So what they said, oh, let's scrape the web, which is Google. What does Google have access to? Tons of web data, web scrape data, sentences, text. So they said, okay, somehow we need to convert this text into something we can use to train BERT. So they used a trick, which is the masked. They used two tricks, but I'll just, in the interest of time, I'll focus on only one trick, because the other trick, they use two tricks. I won't mention the other trick because we don't have time. And also one of the findings of Roberta was, it is better if you don't use the other trick. An improvement on BERT was that we shouldn't use the other trick. So we'll use that. I'll just teach you. What it says is that take the sentence, the cow jumped. Go and mask a sentence, mask a word, right? So now what do you say? You get X is equal to the mask jumped over the name. So this will go into the encoder, right? And you will get the token HCLS. One vector, you'll get one vector. Now you have a vector. Pass that vector into, do a few feed forward, etc. Some basic transformations if you feel like it. And then pass that into your softmax, let us say. Softmax for each of the words in the dictionary. They took about 30K words, vocabulary, a vocabulary, vocabulary of approximately 30K words from aardvark. Let's say aardvark down to whatever is the last word. Zakar. Are we together? And then you create a softmax for that dictionary, for that vocabulary. And what will this produce? It will produce the probability of all the words, right? So then, but you know what the real answer is. What is Y? Cow. So you just ended up creating labeled data, isn't it? By using the masked language model from plain normal text, you ended up creating a labeled data situation. Are you following me, guys? Right? So now we have a X, Y. This now has
a sentence into two parts, the X and the Y.
Exactly. And therefore you have now supervised learning. Means this is input, that is out, that is what the output should be. Go ahead.
So when you provide the sentence, so you just say the jump over the moon. Then you're expecting the cow jump over the moon now.
Yeah. So what you want is the probability of the cow should be highest.
I think the question was when you talk about the mask sentence, you're masking that particular word.
Yeah.
You're providing the jump over the moon.
No. The mask jump over the moon. You replace the word cow with the token called mask.
Oh,
right.
Thank you.
So this, and now you say that if I take the CLS token and then I feed it to a softmax, which word, the word that I want to light up most is cow. If something else lights up, I have a loss, isn't it? So suppose the probability of the cow jumping over the moon is low, right? Suppose it comes out to be 0.1. What will happen to my loss? At this moment, I know. If P cow is 1, let's say, then how much is my loss? Log of 1 is 0. So if P cow is approximately 1, then log P cow 0, right? No loss. The machine got it. On the other hand, let's say that if P cow is 0.01, 10 to the minus 3. Now what happens? Minus log 10 to the minus 3 is 3. Let's say that we are looking in powers of 10, but in reality, you look in natural log, but okay, let's oversimplify. 3. That is meaningful loss, right? That's quite a bit of loss, right? And therefore, you can backpropagate the loss and adjust the knobs in the transformer to do better the next time. Isn't it, guys? That is it. So we have a masked language model technique. This used to be in the old literature also called the Close technique. Right. Now we just call it MLM, masked language model. Right. Very different from multi-level marketing.
But this is a brilliant idea.
Yes, right. Brilliant idea, exactly. Now they used another technique. I'm deliberately not telling you about it. Or I might as well mention it. See, what they did is you have the cow sentence A followed by sentence B, right? They would feed. Remember, you had the ability to feed 2 sentences, and what you had to do is predict the probability that B follows A. So what they would do is they would take a real sentence and a real B that actually follows. They wanted this probability to be high. They would take A and put some random sentence next to it, and they train the machine to predict a probability that is low, right? Because then it would be forced to understand semantically is the second sentence related to the first one, entailment kind of thing, right? And then
this is what we did in sentence work.
No, we did something slightly different. We'll come to that. We'll come to that. See, guys, this field of machine learning, at heart, it's about 3 core components. Creating an architecture, designing an architecture, neural architecture. Once you have done that, designing the loss function. Based on what you put in the loss function, you get entirely different behavior. You train the machine and the same neural architecture to do different things. In the sentence BERT, you actually use BERT that I'm teaching you, but you change the loss function, right? So it does what we wanted it to do in the side. But here we're talking of the vanilla, just out of the box. So this part, by the way, is really important. All of this field boils down to putting together, thinking through a neural architecture, thinking through a good wiring of the machine. Right? And quite often you wire the machine by continually unwiring and rewiring here and there. In physical terms, right, it's literally like, imagine that you're sitting in a data center and you're asking, what if I take this wire and then route it that way through that network and then through this? Somewhat not very different from that. People just go about wiring and thinking up neural architectures. Once they do it, then the whole question is, okay, what do we train this machine for? What should it do well? That is your loss function. And once those 2 things are done, then the rest of the thing is relatively straightforward. Then you do some hyperparameter. I mean, it takes a lot of time, a lot of fiddling, but basically the 2 core games that you play is wiring, and loss function.
So
Designing a loss function.
in this case, like the last function is negative log of probability. So
Yes.
but the way how we are providing the x and y is else. But the last function is the same.
Loss function is the same. But the loss function for the use case that Prasanna brings in, which was that boot camp's loss function, that loss function is different. That, remember, was called the contrastive loss. Whereas here we are dealing with the very simple negative loss, negative log loss, NLL. Negative loss. Literally that. Isn't it?
Yeah.
That's what we are doing. Simple loss. This is the most common loss use log function. Right? So now this machine got trained. Once you train this machine, now think a little bit about it. Just sit back and think. If a machine could learn this, how would it know what in the world jumped over the moon? For it to do, it could have just said the running jumped over the moon. Right? The great jumped over the moon. It could put verbs there. It could put adjectives there. It could put adverbs there. It could put is there. The is jumped over the moon. Right? It could even have put a punctuation there if it was making random guesses. But it has to know that it needs to put, amongst other things, a noun there. And somehow cows are much more likely to jump over the moon than, let's say, trucks. Right? In human literature, because in children's stories, it turns out cows jumped over the moon. Does it make sense? So for it to get that right, implicitly, it has to decipher and get a sense of human language. Isn't it? Are you seeing that? Otherwise, there is no way. One cannot, just in the abstract, think about it. A machine cannot put cow there unless it has a general sense of the human language. And if it has a sense, therefore you have modeled that, you have a good language model. Do you see that? We just produced a language model, and that's a clever trick. See, what a simple trick we used. The research paper, Bert used just a mass language model. And thus are great ideas born, great architectures born. The simple idea, you say that if I force a machine to just do this, it will be forced to become a language model. Right? A good language model. Right?
Is that so? It's like a hop game. It's mask it and find it out.
Yeah, it sort of has the flavor of it. See, there's a lot of similarity between a lot of these ideas. And the thing is, you guys are learning a lot of this at a fast pace. So I can imagine that wires are getting crossed here too. So, all right, guys. So that's good. Now, before we conclude and take a break, let's look at what you can do with this. Suppose I send in a text. Forget. So I could send 2 sentences. But I may choose to send only one, right? I get a hidden CLS state. Now, once the machine is trained, I can sort of fine tune it to different tasks. For example, suppose I want to do sentiment analysis. What could I do instead? I could once it has understood the language, now I can take another data set to further train the machine and say this sentence and just give it one sentence, and give it so this is your X, the whole sentence is X. And what is Y? It's a sentence. Yeah, happy, neutral, unhappy. Right? Thumbs up, thumbs down, positive, negative, or something. Or more than that, you could make it for sentiment analysis, you could make it angry, sad, sarcastic, or whatever. Sad, angry, sad, satisfied. You can pick whatever box you want, a set. Or you could just make it thumbs up, thumbs down. Right? Binary. You can pick some sentiment collection. And you realize that all you need to do is take a lot of customer feedback or that kind of a thing, rating data, And now it can become a sentiment analysis. And for sentiment analysis, these machines do fairly well, very well actually, these days. So one task it can do. Another task. Suppose I want to classify this sentence. For example, I can classify it by saying, which subject does it belong to? Right? Subject detection. Let's say I have subjects like history, politics, religion. Right? And after being done with the 3 fictional subjects, let's get to science. Biology, math, right? And you may choose to classify the text into each of those. Bring your data, train it further. You could do that, isn't it? And therefore, or more broadly, from there now you can generalize. You can use the BERT architecture good classifiers. You can use it as classifiers, isn't it, guys? Does it make sense? You choose your target space, bring your data, further train the machine, and you'll get your behavior. And it's very effective, actually, very, very effective. Right? You can do a spam detector, and so on and so forth. You could do a language detector. You could do a language, like which language is it? Natural language detector. English, French. Are we together? And so on and so forth. You can think of a whole set of classification tasks that you could do. Let's think of something else you can do. Remember that there are 2 sentences. Suppose I put one sentence as a question and another sentence as a potential answer. Then I can give data in which the X is this pair, right? X is Q, A pair, and Y is whether A answers Q, right? Are we together? So you can give it lots of training data where A is actually the answer to Q, and also in the mix, A is not the answer to Q. Some irrelevant statement. You can do that, isn't it, guys? And so you can tell whether this answer, the second sentence, does answer the first. Or sometimes you can just do sentence 1, sentence 2 as X, and you could ask, why does S2 continue logically S1? Right? So, for example, if you are saying, tomorrow I'm going to wake up in the morning, have my breakfast, and the next sentence says something quite different. It says, one of the activation functions is GILU. Now, that sentence is a non sequitur, isn't it? It has no relevance at all to the first sentence. Does that make sense? So you can make detectors for whether one actually follows from the other. Yes.
So this would make graders, paper graders obsolete.
Oh, forget, human beings are getting obsolete, generally. we are going to be the assistants to this AI. No, I'm kidding. I'm just kidding. By the way, it hasn't happened. See, if this was discovered in 2018, those graders are still around. Right? But it is true, and it is true that in the educational system, the use of AI has exploded in reviewing the answers that people submit. So now almost all grading in many of the places is AI assisted.
It's all depends on like the pricing.
What's that?
It's all depends on the compensation.
Compensation,
Like the stores are getting like for $50 per hour. If the machine can do it like $8, then obviously yes.
That is it. Yeah. Okay, guys. So this is about BERT and its family. It led to Robert Distil. Then people said it's too big a model. Let's teach a student model to be smaller. Then distillation came in. Distillation is a concept I'll explain later in the next follow-up workshop. But yeah, distillation. But let me look at the decoder part. What if we just use the decoder part? Right? Albert.
So you gave a sentence, one sentiment analysis.
Yes.
So so while I'm training, so I have this sentence, and then there are 3 or 4 options that I want it to provide an answer.
Yeah.
So how would I specify those answers?
It's very simple. Have a simple CSV file, let's say, hypothetically, sentence and sentiment. So here it is. I hate the product. What is the sentiment here? Unhappy. This is an unhappy customer, isn't it? That is it. You keep on giving lots of data, as simple as that.
So you give two sets of data. One is a sentence and what it actually means when you train it, and then after that you'll be able to.
Yeah. So what you do is, and this brings up an interesting concept. See, what you do is when you get BERT, it has been pre-trained using the mass language model. You take a pre-trained BERT and then you further train it on for your task, downstream task. The word people use is fine-tune it on downstream tasks. And therefore the word, the 3 crucial words that come in, transfer learning. Transfer learning says you don't train the model from scratch. You cannot train a whole transformer architecture with just, let's say, 10,000 rows of data. What you instead do is a transformer that has been pre-trained model. So there's a pre-training phase, pre-train, very expensive, followed by fine-tune to a task. Are we together? Now, fine-tune. Let's look at that. This is pre-trained. Let's do a contrast here. When you pre-train a model, this is done with web scale. There's lots of data, isn't it? It is unsupervised, means nobody sits and writes a label for all the sentences. What do? You use a clever trick to somehow produce XY labels out of it, isn't it? Computationally expensive. Computationally expensive, time consuming, fine tuning, much smaller data sets needed. Sometimes, 100 rows are, the 100 to 10,000 rows are more than it. This is supervised and computationally far less expensive and not so time consuming. In fact, it is pretty quick. You can quickly fine tune, and you will in the lab. You guys will actually fine tune these models. Are we together? You will take BERT and you will get data and you will fine tune these models. So it will actually be something you can do on the hardware here and support it.
So the both kind of models are open source.
Yeah, all of them are open source. Yeah, they are all open source. Are we together, guys? So now let's look. I think it's 9 o'clock. Should we take a 10-minute break, guys? Then we'll do decoder family of models. And then I would like to show you, give you at least a taste of multimodal models like visual transformers, diffusion models, and so forth, if time permits. But before that, I'll give you guys, before you go for break, please pay attention here. Just 1 second. I want you to go to the course web portal while you're still here, please fill up the workshop feedback. In the 10-15 minutes, please fill it up, and then we are going to make progress. It is important, guys. Otherwise, if you don't do it now, you'll never do it. Please fill this up. It's the last day. Let's do it. All right. So once again, guys, in case you missed what I said, please go and fill this workshop feedback form on your course portal. You'll see this workshop feedback. Let's preview the questions and see if it makes sense here. Yes. Yeah. Somebody have ice cream. Oh. So, yeah.
Something. So basically, like, the machines need to produce something. When the machine produce something, you need to compare it with what is produced. And so, okay, maybe see. It's good, yeah. No, no, that's actually, that is one of the campus. See, you have it, an article, you have the use the article to produce something. So, produce the production is zero. You select any word you can mask. You can mask anywhere. You can mask like a jump, cow. We did say this, but the thing is that you need to have lots and lots of data. So the data has to be real. So if somebody is going to sit and do those things, find the word and mask it, rather they have to do it like a programmatic way. Because they have a lot of spread data from the web. And they write a small program. Okay, take the word, there's no also eligible. And you know that mass things, and when you do the programming of those things, you know which word you have asked for sentence. So then you are creating a massive data set. So now you're going to feed them. You feed them, you know that when it is producing a word or missing word. In the first time, it might have produced something randomly out of the 30,000 words what they have. Right? So now they are comparing. So when they compare it, now you do something like some random word. Your last time. It's that's a right. That's up to us. You cannot make the master same way again and again. Doesn't make any sense. Yeah, you can have like exactly. 10 word sentence. Okay, which means that you can produce 10 sentences. Each one will have different word masks. So at the end of the day, you say, okay, yeah, it has to be like use all the time in the right place. So that gives them more confidence. So and more like kind of like a few different words. Probably like just the ways understanding all these things. For the inference is it's good to do what the example is not giving sentiment analysis. So for the sentiment analysis, you should have the language understanding. Because you write that one on a lot of your sentences, you have the nuances, the meanings, and the semantics of the language. Right? Now we're going to find you for the uses. So you use it. I want to do a sentiment analysis. Okay. What are the uses? You can take the word because it's not a good job. Now I'm going to create a smaller data, which is a sentiment analysis. Now I know based on my product customer feedback, I have it. You can create the data set and those labels. You get trending because by giving the word in the sentence, it knows like what the what means is there. But that is but the sentence itself, because already we try comments. Meaning of the sentence, meaning of the language. It might lose a sentence per se. It has an understanding of like what it means. If somebody says that okay, I paid you, so probably it knows like what it means. But you want kind of grounding to say that okay, what answer I want all of it. That's why you're doing it. Okay, for this kind of words, I want my purpose of using this is to do the sentiment. I don't take the label. The label should be this in this class.
Fantastic courses. The same version, the lab, is so that will be around the same time frame as the advanced boot camp. They run concurrently like this one. That's it. And this will also be in 1600.
But for the new batch, they will have the option to do theory and lab together.
I see.
So they can do Tuesday. For you guys, the lab will be on Thursday.
Okay.
And then Tuesday class will start. And the people join the clinical lab, they have a choice to wait for the next. Yeah. For the
Or they can go on Thursday. So I think have you opened the enrollment for that one?
I'm not opening the enrollment. I mean, I've formally said that if people email it and they then I'll enroll.
I've been told for the advanced. No, but this lab one on Thursdays. That also is.
Oh, it will be, of course. So all of you guys in this class should that.
Should I separately go for that?
But similarly, mind you,
In fact, what I do, I just put down deposit add-ons. And by when are we paying the full fees as well?
see, depends on people's. See, one reason I tell that pay before the last one of the course, and the reason is that if people have no job, then if they get job in between, they can reimburse it from the employer. But if you have a job, then there is no reason to delay. Right?
So then I just want to use and pay for the non-camp employees. Just give the people. This was the land is so useful. One is the theory. Both having man, I find this very powerful way of learning, right? When I spend the next 2 months really trying to
You go deep, use the sun. See, there's a reason I'm not teaching in the sun. Because people need time just to sit there to repeat. And that's why I'm offering all these so-called free courses. I'll be putting a lot of effort to make sure that people review all this. And I hope people attend, they don't just disappear. Yeah, because see, if they in the summer they don't stay engaged and show up in the fall, half the things would have evaporated.
By the way, I managed to get a 4090 card. I asked quality to give me some.
He built you as a night,
So I installed it.
good. Now, like, see, I can't say that officially, but basically you don't learn unless you have a machine under your table. And you can tinker with it and do things.
So the project, we got at a certain stage and discussing that after this mission. We continue. Yes, that's right.
That's the thing.
If they don't access to that machine, this company that problems.
Oh, you want to do it on your machine, the machine that you own.
So that's already built.
So you don't need this machine then.
So once this is over the course, you can tell my machine and whatever we can come to.
So this machine, by the way, for all the team members, I'm saying that they can continue to use it in the
Another
summer.
4 weeks.
No, for the throughout the summer. Okay, but with only one condition. Machine will get free. They need to cover the electricity.
So I'll have to buy the cost of that. So
We will know because summer is a demand price. My guess is that per person it will be somewhere between 13 to 30 cents per person. These machines are paying thousands of dollars in industry. But that's why I'm saying that. Use the machine. I've already paid for it, and now just cover the electricity.
good. Really looking forward.
All right, guys. Can you hear me? We are going to get started with the session now. Are we all done with filling up the feedback form, guys? Guys, are we done filling up the? Anybody needs more time? Raise your hand. You need more time, huh? Okay. Okay. Let's take 5 more minutes. So, a bit of an announcement while you're doing it. I'm assuming that almost all of you would be spilling over into the lab part of it. The lab part will happen on Thursday. From the first week of August, every Thursday, the labs will happen. Now, obviously, there's always the curse of forgetting. So for you, the repeat of this, like the Tuesday will be again from August, the same course repeating. And all of you will have free access to that course. In other words, you can repeat the course for free, the Tuesday part also. Are we together? Right? The Tuesday part, you can repeat. for free. I highly encourage you to repeat the Tuesday part, because then the theory will be fresh in your mind when you sit for the lab on Thursday. Does that make sense, guys?
Question, Asif. So
Yes.
we have boot camp that's on Sunday, and then we have this course. So what's the correlation for the lab that you're talking about for August comparative to the boot camp or the advanced boot camp? How does it all play together?
See, the boot camp is very practical things based. It started, for example, with, if you remember, there is nothing we did with autoencoders, nothing we did with GANs, with convolutional networks directly. I mean, we sort of did some things, but not much with UNet, only tangentially which touch upon the topic. The core architectures, we didn't use at all or touch upon at all. We stayed in a very practical territory. We went from semantic search to RAG to multimodal learning, image transformers, clip, and diffusion models and so forth. So that track is completely devoted to let's get some things built. The lab is all about every neural architecture, because these neural architectures are used a lot. Feed-forward networks, convolutions, recurrence, autoencoders, etc. They have wide applicability, but none of these we touched because, well, of course, the title of the bootcamp was LLM, if you remember, LLM projects. So it only used LLM, whereas the subject is much broader, and all the other neural architectures we cover in the lab for this course. If you notice, everything we covered in this course, we actually did not do in the bootcamp. Bootcamp was all about LLM. So does that answer your question?
Sorry, just getting back to my mute button. Yeah, that does. That makes a lot more sense. Thank you. Did you hear my reply also?
Oh, yeah, yes, it's fine.
Oh, you just paused, so I didn't know if you were still waiting for me to reply.
Yeah. So in this course, in the lab version of it, you will do all of this. You'll do labs in neural style transfer. You'll do labs in data generation, synthetic data generation. You'll do labs in, all of those things like, the style GANs, etc., to generate fake faces. You'll do data compression, autoencoder. You'll do convolutional neural nets and build classifiers from scratch. You'll do a lot of very practical things with each of the neural architectures that happens not to be an element. So while you guys are filling up the feedback form, right, just a bit of a feedback. I feel that I've been more or less a student all my life. To you guys, I appear as the person sitting here and teaching you. But the reality is I myself am a student. All the time, new things keep coming up. And those of you who are physically here have seen that pile of papers. Every month, by the time the month ends, and today is the last day of the month, you can see that huge stack of papers. There is no avoiding it. The subject is exploding. And a bit of a historic thing. In 2018 or 2019 now, for the first course in neural networks, 2018, In one course of 12 weeks, we covered all of neural networks. At that time, and transformers had just come about. We just touched upon it. We mostly did everything that we are talking about now. And it wasn't so deep. Everything was still taking off. And neural networks were the hot topic, just as today, LLMs are the hot topic. What a tremendous amount of ground has been covered in the last 7 years.
This regarding that we started when we discussed about, so Google is using TensorFlow and Facebook, the PyTorch, because of the popularity PyTorch getting.
Yes.
But I heard from the people who the Tesla, the autopilot and everything, they use a C++ behind the scene. I mean, they are not using. So like that, how many industries apart from PyTorch and PyTorch and TensorFlow, it's like they use the raw.
Good question. Let me mention the question before I answer. I have a question here that asks that Tesla doesn't use either TensorFlow from Google or PyTorch from Facebook. It uses just C++ for its algorithms. So how many other industries are there which just hand create their AI algorithms from scratch? So the answer to that is, first, TensorFlow and PyTorch, both of them are written in C++. And the reason they run so, you can't write code in Python. Python is just the user interface to those very heavyweight libraries. Almost everything that is high performance and computationally intense, there are only 3 languages that they are written in. King of the hill is Fortran. You know, when you use scikit, numpy, all of that, you may not realize, but you're actually using Fortran. Fortran used to be the library that my generation, when we didn't have YTR, used to build. Then came C and C++. C was considered in those days rather slow, obviously compared to Fortran, but now, of course, nobody says that. C++ have caught up, they're very fast. But then Python is, of course, horrendously slow. Nobody in his right mind would write a full machine learning library in Python. Now there are a few new kids on the block. One of the languages is Julia from MIT that gained some traction, but for some reason didn't take off as widely. The other language that's beginning to take off is Rust. Right? Hugging Face, for example, has adopted Rust, if I'm right. I'm pretty sure they have. And in fact, when you come to the LLM2, you will do some exercises in Rust. Rust is closer to C++. And a lot of companies are doing that. Now the last part of your question, how many industries are writing their own in C++? Complete machine learning libraries from scratch? Almost none. What Tesla is doing with his autonomous, and this is one of the paradoxes. People think of autonomous self-driven cars as one of the prime examples of AI. Actually, it's not. Autonomous self-driven cars use very, very, very little AI in the actual decision. They use computer vision and AI in the perception part of it, and image segmentation and so on and so forth. That part they do. And that part, I'm pretty sure they are not reinventing the wheel. They're just using OpenCV and these computer vision libraries and PyTorch and so forth. But for their own, the rest, actually, the responding part, they would have written their code in C++, but that makes sense. AI libraries are not very easy to recreate. It's a very deep technical stack. Very deep, and its roots go down to Fortran in many ways, libraries in Fortran.
Yes, stick with PyTorch.
Absolutely stick with that. If you want to go faster, write it. Just go to the C++ library of PyTorch because it's written in C++. Not many people realize that you can do PyTorch in C++. So you should do that. All right, guys, should we start now? Are we all done? Anybody still needing time to finish the evaluations? I'll get started. So guys, I would request you an extra hour today. It's our last session. I would like to finish it with something. So we talked about transfer learning. By the way, is the recording still on or off? Let me see. I may have forgotten to, did I even start it? I don't remember. What happened to this? Give me a second. Oh, it is live streaming. It's been live streaming all the time. Okay. So transfer learning is about the new way that we do things with big models, because it's not practical for us to train these ginormous models. The new paradigm is you always have a form of transfer learning. The big guys will pre-train a model. That will be an exercise in web scale data with unsupervised modality, but somehow you use a trick to create label data out of it to train it, like the mass language model. These are computationally brutal things. Typically, you use a cluster of servers, GPU servers to do it. Very time consuming. By the way, how expensive are these things? People are spending close to $100 million to train some of these ginormous models, transformer models. That should give you a sense of the scale. 30 million, 40 million, 100 million. These numbers are difficult to believe to train one model. And there's an environmental cost too. Imagine the sheer amount of electricity that goes to train a model. These models are often called foundational models.
You're not sharing.
Oh, I am not. I apologize. Okay, 1 second. And what happened to, give me a sec. The Zoom is continually getting into a corner. Okay. Any better luck? Am I sharing it now?
Yeah.
Apologize for that. So these models that are trained with great effort and great cost are called foundational models. This term, I believe, was coined right here at Stanford in a neighborhood college, I suppose. Right? So, who is it? I think it was Fei-Fei Li's group that coined the term foundation model. So foundational models get created. Then you fine-tune it for specific purposes. Fine-tuning is a much smaller game. You can fine-tune it with small data. So usually supervised, you have some label data to do it. Computationally far less expensive. And it doesn't take that much time. Now, some models you can fine-tune on your workstation. Some models you can fine-tune on a GPU server. Some models, unfortunately, still need a small GPU cluster. But small is the operative word. Okay? You can do that. Model fine-tuning is something, those of you who are taking the LLM bootcamp, you will see that we'll be doing it extensively in the fall. You'll see we actually have a full course on model fine-tuning, but that's for LLMs. Now comes, with that there, I would like to speak for a moment on the environmental cost of all of this, guys. Because see, we are delighted by the power of these models. There's a leaderboard for this and leaderboard for that. So, oh, by the way, I don't know, these days, today's rumor, did you guys know that apparently GPT-5 is out, but it is skulking in the guise of GPT-2 chat.
It's better.
Yeah, and it is, well, it seems to be doing quite well from all the feedback that we are hiding. So, well, so all of these models are quite impressive, and it's a testament to the amount of energy, creativity, mathematics, and like innovations that have gone into it. But the one thing you also have to remember is that there's a huge environmental cost to it. It takes the same amount of electricity as would power a small city to train one of these models.
Not only electricity, the heat is producing also they use a lot of water.
Massive, yes, massive amount of heating, right? And CO2 footprint, carbon footprint of these models is shockingly high. Therefore, wherever possible, of course, you should reuse an existing model. Most of the time, smaller models will serve your purpose. Don't use a big model simply because it's a one-upmanship. Oh, you're using only a 7 billion parameter model? I'm using a 70 billion parameter. Only 70 billion parameter. Oh, I'm using a 300 billion parameter model. There's a lot of one-upmanship, and actually it's unnecessary. One of the things that's emerging from research is smaller models quite often do very well. There is a neural scaling law. Bigger models are more capable, but find if for your particular task, is it really necessary? It may not be. Ultimately, you may reach a point of diminishing returns. A 10x bigger model may just get you 1% gain, and it may not matter in the field, in the business situation. So that is something worth remembering. Okay, so with that now I'll conclude by giving you, let me talk a little bit about the decoder-based models. The ones that don't throw away the decoder, that have the decoder. So you have two architectures. So you have the encoder, feeds into the decoder. What does the decoder do? It produces an output, but the output also feedbacks into the input of the decoder, right? Then we have decoder. What would be the loss function for the decoder? It's much simpler. So suppose I have a sentence. Let's say it was let's take a sentence like this. What could I do? I could, let us say hypothetically, start with stop here. I feed this into the system, right? So it becomes some latent representation. Then you ask this decoder, say something. And let's say the decoder will produce some word, some probability map. It will produce some word, and that word will have a certain probability, isn't it? But what do you expect? You expect the word times. So ultimately, because there is a softmax here, softmax, you remember your softmax. What is the softmax against? The vocabulary in the decoder, right? Vocabulary. So you just have to go and look at probability of the word times, because that is the word that you want. If that is low, you have a loss, isn't it? So it is a negative against log p, the word that you want. Does that make sense? Because if it says times, I'm 100% sure it's times, then there is no loss. It is machine has learned. But if it says it was the best of horses, well, probability of times is very low, then now you have a problem. So you do have a loss. So you can keep on doing that. So now let us say that by chance, it does produce the word times. Now, let's say that, let's take two situations. Let's say that it produced, the most probable word that it produces is horses. Right? It was the best of horses. Looks somewhat sensible. It was the worst of horses. Okay. So now what happens is you do have a choice in these machines. Do you feed the word horses back here? You realize that you have a choice. You can put the word horses. I'll put a had here. Had to me, that was the prediction. Or you could feed the word times. So even though it made a mistake, it said horses, you still feed the word times in the next time and say, okay, now I'll give you this much, predict the next word. Are we together? Or predicts the next token, rather, the semicolon, do that. So when you feed the right answer, that method is often called a teacher forcing function. Right? You should be giving horses, but you are giving times because you're continually doing course correction, isn't it? So that's how you train the decoder. That's how decoders are trained. What will decoders do? Do you realize that decoders are generative? They are very good at generative tasks, right? Decoders are good at generative tasks, whereas the encoders are good at classification, discriminative tasks. And as those of you who attended the boot camp know that we can also create good semantic tasks, word and sentence embeddings and so on and so forth. But we won't go there. But discriminative tasks we saw, we can use it for classifiers. Right? Decoders are generative. And therefore, what can you do with it? You can, of course, generate what are called continuations. So the next word, that next token, next tokens, they are what? Continuations. But a continuation could be answer to a question. Answer to a question, isn't it? It could be an explanation. It could be an essay. It could be, for example, it could even be a translation. It could be a translation, isn't it? It could be converting your text into a haiku. And by the way, you can try it. In the labs, you will try it. But you realize that the continuations could be a whole variety of things. Or it could technically also be used as a classifier by saying, yes, just answer yes or no. Right? Or given a text, you can treat it as a classifier. When you do that, you'll realize that for classifiers, and pure encoder-based models do better than decoder-based models. Yeah. But you could potentially use it. So with generative machines, you could do a lot of things. And obviously the decoder is the crux, very much like the variational autoencoder, very much like the generative adversarial network. The moment you keep the decoder, you are looking at a generative model. Right? GPT started out like this. It just started with a decoder. And then nothing prevents you from having the full transformer, like encoder, decoder. Use it all for both generative tasks. Because in other words, so long as you have a decoder, you have generative. Nothing prevents you from putting the encoder also. So things like BART belong to this category, right? T5, etc., etc. There are many models which are which use both encoder and decoder with pretty good results. Right? So you will find that in the transformer architecture, there is a fork in the road. Some architectures are, so three types. Encoder only, very good with discriminative tasks and semantic understanding. Decoder only, generative, encoder, decoder, the full transformer, decoder, also are generated. And then as you go through the boot camps, when you come to the boot camps, you'll realize that there are all sorts of mixtures of these. If you guys remember your blip, anybody here taking the boot camp? You remember blip, clip, blip, etc., blip, lava, and so forth. Those are very interesting architectures. So that is that. So there are three basic types that you can do with the transformers. But now comes text is okay. Let me end this discussion with multimodal. So what happened is something very interesting. CNNs were sitting upon the computer vision tasks. Transformers they topple the dominance of RNNs, LSTMs and GRUs. People began to ask, if the transformers are so insanely powerful, can we not use it for vision tasks also? But there is a problem. I'm looking at the picture of a cat. Where are the words? You need to somehow first convert it into words. Right? But why would it work? So let's sit back and ask, how we'll do it is a different question. Is a picture a language? People do use the phrase that a picture is worth 1,000 words. And you can even argue to the extent that language is a means of conveying something, communicating. Words communicate. Different people communicate with different words. Right? And even within English, see, the same thing may happen. Let's say that the mangoes are ripe and beginning to fall from a tree. Well, the English-speaking people would use entirely different words to describe the situation than Tamil-speaking people would do. And the Tamil-speaking people would describe it in an entirely different way than, let's say, a Mandarin-speaking person would do. Make sense? And so on and so forth. But at the foundation of it, the semantic is the same, meaning is the same. And what these transformers are good at is getting to the meaning of it. So one of the very interesting experiments that came and became quite a bit of news is people trained the transformers, for example, to translate from English to, let's say, French, right? They trained the machine to translate from, let's say, English to German, right? Or something like that. And gradually they began to notice that the machines are developing the ability to translate from French to German. Why? Because the semantic content is the same. Obviously, it makes sense in hindsight that it would be able to do that. Right? So if transformers are going to the heart of the matter, the meaning of things, well, I can convey the meaning with a picture or with the audio. And therefore, a picture is also a language. It's a form of communication, a medium of communication. A video is again a medium of communication. Audio, of course, is very directly a medium of communication. We speak more words than we write, by orders of magnitude more. Right? So the question therefore is, are transformers about the essence of the language, or are they dependent on specific realizations of the language as words? And that is the question that was resoundingly answered by one of the landmark papers. The paper was and we will cover that in the boot camp, so not here, VIT. And in the practical part of this will end in the last session of this lab, in the practical one, also will cover. What people did is they looked at this picture. Let's say the picture is of a cat. I keep saying cat. In the practical part, we'll have lots of cats and dogs to hound you. Right? You'll work with the famous cat and dog data sets a lot. So we have a cat. And let's say that there is a bird sitting upon a cat. Does that look fair? Sitting upon a cat. And cat is sitting upon something. Now I can take this picture and I can slice it up. What people did is they said, okay, let's slice it up into 16 cross 16 pixels. Are we together? And then they said, let's see, think about it. It is like a jigsaw puzzle. We all play this jigsaw puzzle thing during holiday season, right? In Christmas time, winter time, it's a tradition. We'll all get a box of jigsaw puzzles. It will be some beautiful picture puzzles. And then we'll put all the pieces together and a beautiful picture will emerge. This paper did the same thing. It said, let's break it up into this little simpler, well, not jigsaw, but square patches. These are called patches. Patch. One patch is 16 by 16 pixel, makes a patch. So now you have decomposed the picture, excuse me. The picture into patches. And now what it said is, let us take this 16 cross 16. It is, what is it? It's basically a matrix of numbers. Each pixel is a RGB value, cross 3. In reality, cross 3, right? RGB value. But let me forget about the cross 3. What you can do is, you can multiply it with a, well, again, a matrix to make it into a linear vector. Are we together? To create an embedding vector out of it. We can do that, right? For example, 16 cross 16, just as this thing, if I multiplied by a 16 cross 1 matrix, what will it become? It will just become a vector, isn't it? As simple as that, right? So you can apply a linear transform to make it into a vector. Right? Once you do a linear transformation of it, now what do you get? How do you know that this did not come from a word? This is not a word embedding, this is a pixel embedding. Like, as far as the transformer is concerned, a vector is a vector, isn't it? Token embedding vector is a token embedding vector. And therefore, you can pass this token embedding vector using this trick, patch 1, patch 2, each of these become vectors, patch n, right? Through this, and now what happens? Everything that you were doing, you can do now. You can use a classifier to tell whether it's a cat or dog, isn't it? You can do all sorts of games with it. And that is and so I'm just giving you the high level ideas, guys, that opens the door to multimodality, right? Multimodal learning. Now you just went from words to, extended the power of transformers to images. And today, there's a fierce competition between CNN-based approaches and transformer-based approach. Transformers are gaining ground. They're doing very, very well. And in fact, the Sora, many of you are aware, Sora, what Sora is? Video generation, etc. They are all using transformers and heavily. And CNNs are still here. But gradually, more and more people are coupling, even if they're using CNNs, they're using CNNs and transformers and attention and so forth. Your question.
So when you compare with the word like it's a token screen.
Yeah.
But when you say patches, in CNN we use the filter to do it. Right?
Yeah, so that whole way of thinking you remove.
Yeah, this is like patches like that also is kind of small pieces of the picture.
Exactly, small pieces of the picture. Yeah, that's literally what it is. Wasn't it?
The advantage that CNN has over transformers is that it's lightweight. It could run on.
Absolutely. CNNs are much lighter. See, one of the issues that people had with transformer VIT was, and now we're getting into the technical bits, is that, hey, CNN had a very strong inductive bias. You had local patches, etc. Here also you have inductive bias, but patches are pay attention to each other, but hierarchy of feature was not there. So the VIT led to an architecture called the swing transformer, which brought about that. What it did is it started by 4x4 patch. Then just as you do pooling in a CNN to get a slightly bigger perception field, it would do something very similar, sliding window. So sliding window should quite a bit remind you of the sliding the filter forward and pooling, etc. Process you would get 8x8, etc. So there is a similarity to it. Today, the state of the art are swing transformers. Well, close to that. They're somewhat like that. Swing transformers, then take lots of the ideas from CNN, hybridize that with the transformer, and they were very effective. We use the swing transformers a lot in different use cases. So that is it. So now let's go, because we have very little time. How about audio? You say, all right, you played some trick and now you got the picture in. Audio is a different game. Audio looks like what? If you look at the diaphragm, the physical, a transducer signal, right? This is the amplitude of the signal, which becomes, so what happens? A diaphragm receives your voice. So I'm speaking into the microphone. This microphone at heart is nothing but a diaphragm, right? Onto which my sound waves impinge, and it has a transducer. The transducer converts that into current. It's a weak current, and then you have amplifiers, like you see the amplifier sitting next to me on the table, that amplifies the signal and then passes it forward, right? So you have this is your time axis. What about this? How would you convert this to words? This looks harder, isn't it? Well, it turns out there's a clever trick to do that. What you do is, there is something called a Fourier transform. And what it does is, it looks at the signal in the frequency domain. Are we together? And what people did is that they would take a 30-second, let's look at a 30-second or some second segment of a signal, sound. That is one patch of sound. What you do is you do a Fourier transform, and then the y-axis is not amplitude, but frequency. From frequency 0 to, what is it, 20 kilohertz frequency, right? So at any given time, different frequencies will be represented more, right? So you heat map it, the magnitude, the value that you put for each frequency, let's say 10K. How strong was 10K frequency present in this signal? Are we together? Right? At that particular moment. At that particular moment, how much was the 10K frequency present? You light it up. So you create a frequency heat map. This is still time, 30-second time. Then you'll have another, then you'll have another, then you'll have another. All of these things. Does that make sense, guys? For every tiny slice of time, whatever the signal looks, you can do a Fourier, and it will tell you what the frequency distribution is along the y-axis. How strong was that frequency present? Isn't it? So, for example, if it is a bird's chirping, the higher frequencies will dominate. These will have high values, right? If it is, think of something low frequency, the rumble, right? Yeah, the thumping of the feet of the elephant on the ground, low frequency, the reverberations of that. Right? So you can create. This is called a spectrogram. So whenever you have a time varying signal, you can make a spectrogram. But with audio in particular, you do something special. You do something called MEL spectrogram. What happens is that the human ear doesn't hear all frequencies equally. It hears certain frequencies more than others. So when you adapt, is MEL part is adapting to the human response, human audio response, because it gets more, we grasp nuances of certain frequencies more than other frequencies. I believe it's the high frequencies that we respond to a bit more. So it sort of is somewhat like a log transfer, something like that. You do a MEL spectrum. So now that I do a MEL spectrogram, what do I end up with?
Spectrogram is like relative. Let's say if we perceive 10 kilohertz more sharply,
Yeah,
then we perceive 10 hertz.
that is right. Yeah.
So then it kind of normalizes.
Normalize it. Just makes it human. But just think of spectrogram. Now, what is this spectrogram? It is basically a image, isn't it? And so from audio, we went to an image. Image, we can go to tokens, patches, isn't it? And so even audio we can deal with. Now things are beginning to look rather rosy for the transformer, isn't it? Let's take it a bit further. What about video? Well, if you can do this, you realize that you can apply the same argument to, well, thermal images are easy. Thermal images, they are nothing but pictures in the infrared spectrum, right? So images are images. Go ahead.
How it knows, like in the normal text, we know in the context, okay, this is what we're going to do. Here also something like that.
It figures it out. That's the most remarkable thing.
It's like taking from sound and we can remove the sound of the brain.
Yeah, yeah. It even can, I mean, this is how audio to text happens. Speech to text has these things built in.
Because of all our number comparison. So
yeah, that is right. Yeah. See, this is it. You know, we build transformers. We have a sense of how to build it, how we think it works, but then it works beyond our wildest dreams. And then we sit back and ask, no, why did it work so well? No one knows. Yeah.
Whisper is using this MEL spectrogram to create the words.
Whisper is using, this is a little bit more complicated architecture, but yes, roughly speaking, the answer is yes. Now, thermal is just an image, so thermal is taken care of. So what are we doing? Text, done. Images, done. Audio, done. Right? You realize that the dominoes are falling rather fast, right? Then you come to video. What about video? Well, video is nothing but a sequence of images and waveform, right? We just did both images and audio. So in some sense, at least we get a start on video with transformers. Video has one extra thing, the temporal information. Yeah? That this frame, A, B, C, G, they're not independent. There's a sequentiality to them, which also you have to be aware of. But essentially, you can do video also. And then there are also depth images. Images come from what? Sonar, etc. Various equipments for depth images. You can do all of that. You see that, right?
So in this context, the relationship between the image and the sound. So essentially, this is all going in as a single encoding with the positional.
Yes, yes, everything, yeah. So the whole technology of the transformer kicks in. Yeah. See, the moment you realize that you can convert bits of the audio into a MEL spectrogram image, you have a winning thing. Position is simple. This is first position, this guy is the number 2, this guy is number 3, and so on and so forth. You can keep going on.
Correlate that first position with that specific position in the image.
Right. Yeah, exactly. And the amazing thing, and so see, because we are out of time and I have just 5-10 minutes left and I would like to summarize this course. I'm just giving you a very high level idea of what is possible. And so all of a sudden the transformer is beginning to look like a universal architecture, isn't it? So you might as well have asked, okay, so why did I waste 10 lectures on other things, on other neural architectures? What's the answer to that? Yeah, you need to have come here, but more than that, those architectures have not gone away. Great things are done when you hybridize architectures. Almost all the powerful use cases, for example, the diffusion model is autoencoders, CNNs, and transformer like attention put together, mixed up. Right? Almost all the great, remarkable things being done use all of them, not just one of them. Are we together? Right? Now, diffusion, because we have run out of, 1 second, before we have run out of time, I won't go into diffusion, but you should get an idea that we can do that. I'll give an extra session at some point. I'll walk through diffusion. And my diffusion video, by the way, is online. You can watch it anyway. But or do you guys want a 5-minute intro to diffusion? Sure. Okay. See, what you do in diffusion is you, first of all, you take the, the autoencoder. Imagine a CNN-based autoencoder, right? But there is an adaptation of it in which you have residual connections. Like you have short circuits. Why we have that, you'll learn later in the boot camps. But basically think your autoencoder. Encoder. This architecture is called U-net because it has the shape of a U because of this up here. So we'll take the U-net, and then what happens is this was initially done using convolution deconv. So what it does is, if you give it a blurry, so let me give you the intuition. If you give it a blurry image, you will get a sharp image. We talked about this. Denoising. So that same denoising autoencoder, you can make it even smarter by adding a few residual connections. So a U-net. Just think of it as a variant of the denoising. So now we have a U-net that can denoise. Now there is a variation of the U-net in which you add attention also. You'll see why. But okay, people started adding attention to everything, to all ConNet architectures. Now what happens is, if I can take a blurry image and I can put a U-net here, sharpen it, sharpen it, sharpen it, U-net, U-net, U-net. Then I should get a really high resolution image, isn't it? And now you realize that I can keep this chain backward. Start with the really, really, really blurry image. Now, what is a really, really, so think of a cat. What's a really, really, really blurry cat? Noise. Right? Really, 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 really blurry cat. And you say, well, I can now produce a high resolution cat out of it. But actually, this is nothing but noise. So how do you know that the machine won't produce a horse instead or a truck instead? Right? You're sharpening essential noise, isn't it? So that's where a technology called diffusion, and I'm oversimplifying it. This is almost not doing it justice at all. But since we have a few minutes, I'll put it here. It comes from non-equilibrium thermodynamics, but thermo. This theory comes from that. But I'll give you a basic idea. What you do is, you take this blurry, 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 blurry noise, and you put a U-net here. But in the U-net, you add attention. The transformer-like thinking. It will attend to a text you give. Right? So you say, cat on the window. Cat on the window. Right? Now, what will happen is this attention, because this U-net, as it is trying to produce a sharper cat, it will be forced to attend to this text. You learned about attention, and this text will guide it. See, from pure noise, it could go anywhere, infinitely many directions, right? But it will guide it slightly towards producing. And if you just do this, diffusion will do it in the lab, you'll see. It will produce something in the first step that looks nothing like a cat. Right? Second step, nothing. 100 steps later, at every time you have a unit plus attention, all of them paying attention to the cat, right? What happens is gradually a cat begins to emerge. And then finally, 500 steps later, a beautiful cat on a windowsill comes out. Right? Now, how in the world do you train this machine? What you do is you start with a lot of good images and their description. So you say, let's start with the cat, the same description. And you keep on. So training is the forward diffusion process. Training is the, so training happens like this, forward diffusion. I take the beautiful cat image and I add a little bit of noise to it. Let me just use the word noise. Noise to it, little bit of noise. It becomes a blurry image, right? And blurry, 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 blurry. I can keep adding noise to it till it becomes this, isn't it? And at each step, I train the unit plus map to do reverse diffusion, means to undo my noise. So the unit will keep getting trained to sharpen and undo the noise by reading the text. Are you getting it? So unit gets trained on what we call reverse diffusion, grounded in the text. And therefore, from pure noise, it can produce beautiful images.
Fundamentally, because noise is random,
yes,
the same image probably gets trained in multiple iterations.
Yes.
Multiple noise components, right?
Yes, yes, definitely. I mean, to train diffusion models is no joke. You start with gazillions of images and texts and then start your journey like that gradually. And when you have a model trained, then suddenly everybody is amazed that you can do it. But guys, I did a very hand-waving argument about how diffusion works. But do you realize that now you're literally, I've entered today's session, taking you to the doorsteps of how some of these most magical modern technologies work. This is the foundational idea, for example, behind things like solar.
What is it? Thermodynamics? What is it?
Oh, this is non-equilibrium thermodynamics. Diffusion belongs to non-equilibrium thermodynamics. Comes from physics, actually.
Yeah.
So, all right, guys, I wanted to take the last 10 minutes to, first of all, it's been a long journey, guys, and I would like to really thank you. It's been fun. It's the fate of a teacher, I suppose. When you sit here and teach, you get attached to everybody in the audience. Okay? You all become friends, and it's hard to believe that I might not see some of you later. But yeah, in any case, thank you for giving me the privilege of this journey, for taking you guys on this journey. I mean it. It's not a cliche. It really means. It's been a journey we took together. I hope I did help you. You all came with some career goals, some career aspirations. I would very much like you guys to succeed in those aspirations. So again, I'll repeat what I've said. I'm available. My doors are open in the afternoon. So usually, and you can afternoons, evenings, you can walk in here anytime. Many of you do walk in here. And whatever it takes for you to succeed, mock interviews, help with your projects that you're doing, but it cannot be, don't reveal your company secrets or company projects, but any hobby projects you're doing, anything, you're most welcome to drop by. And I'll be happy to help you. And do stay in touch. And I hope it has been a rewarding journey for you guys. And with that, I'll conclude. Thank you, guys.
Thank you.
Thank you so much for inviting me.
Yes, likewise. Thank you. It's really, really fun that you guys are here.
When they go into the college,